Hi, I'm Ben-Yaakov. This presentation is entitled Inductor Discharge Answer to Riddle. This is an answer to a riddle that I've posted earlier, and here is the riddle. I'm showing here a situation which looks like a paradox, and the riddle is to explain what is really going on. So here is the setup. We have here two different ways of driving an inductor. This could be a solenoid, a relay, or contactor, which has a 100 millihenry inductance and then some DC resistance. This is the conventional way. We have a transistor, a MOSFET, and then we need a diode to capture the current when the transistor is off. Otherwise, we're going to have here very high voltages. I've also added a resistor such that the voltage developed here, the negative voltage, will be a little bit higher than just the drop on a diode. By this, the current will drop faster than just with the diode. On the left side, we have a different topology for the same purpose. We have here in the inductor, then there is a resistance, the same thing here, the same source, we are driving it, and then it turns on, and the current, of course, will build up as here. And here, I also have a diode, but notice that this is a very large resistance. As I'll show later on, this really doesn't matter. If I would have put a resistor of large resistance in this case, then all this current coming through this resistor will build up a very high voltage that may damage the transistor. As we will see, this is not happening here. So let's have a look what is really going on. Here I'm showing the current of the inductors. This is the conventional topology. This is the current of the inductor, and this is this one which goes down as would be expected exponentially when the diode is capturing and there is some resistance, both of the 2 ohm and the internal resistance, which is small. And then we have the current in this case. It's also building up the same way. I've adjusted so it'll be the same because it's the same inductance, same resistance. But you see that the decrease is different. It's actually linear here. Okay, but that's not all the differences. If we look at the current of the diode or the resistor, in the conventional case, we see that the current goes to the current of the inductor. In this case, about 500 milliamp. Same thing here because it's the same current here. And then it drops exponentially, exactly like the inductor because it's the same current, okay? But look what happens here. If I look at the current here in this diode or resistor, it's only 2 milliamp. So with the 1K resistor, the voltage drop is only 2 volts. That's it. And it's a different behavior altogether. So this behavior here is really very much different from what you'll see here, although it sort of looks the same. So here are the question of this riddle. In the sourcing topology that I've shown, the questions are: why is the resistor current low? Where is the inductor energy dissipating? And what are the options for changing the current magnitude? In my answer, let me start off with the input characteristic of the MOSFET. This is the gate to source voltage, and this is the current, and I'm showing the range of interest that will be discussed in this video. So we see that the threshold is about 2 volts, so that up to 1 amp, the voltage VGS is about 2 volts. So let's go over the sequence of turn on and turn off of this stage in which the inductor is in the source rather in the drain. So I'm starting off with a 0 voltage at the gate here toward ground, and of course everything is 0, VGS is 0, voltage on the transistor is the 5 volt here because the transistor is non-conducting, and there is no current, so everything is 0. That's fine. So let's move to the case in which the gate is 10 volts. Okay? In this case, the transistor is conducting. There is a 5 volt here. Transistor is on. In fact, the voltage across it is 0. so that the inductor now is being charged through this 5 volt. We see here the charge of the inductor, and then the current is going up to say 500 milliamp, and in this case the gate to source voltage is 5 volt, and this is because the transistor is on, so this voltage here is like the 5 volt here, we have 10 volt here, so gate to source is 5 volt, transistor is conducting, of course, it's in like RDS on here, and this is like an on state. So let's move now to the more interesting case in which the transistor is turned off. Okay, we've been at 10 volt, now it's going down to 0. So we are interrupting the current, and due to this fact, the voltage here at this point starts to go negative because of the IDT. As it goes negative, it'll hit eventually the 2 volt or minus 2 volt, and then the transistor will start conducting. So we have a situation now that the transistor is in fact conducting. There is 2 volt here. Voltage on the transistor is this minus 2 volt plus the 5 volt is 7 volt. The voltage on the inductor is constant. It's 2 volt or minus 2 volt. Therefore the current is going down. The voltage across this branch here is now 2 volts, and the current will be accordingly dependent on the size of this resistor. We'll see it in a minute. So let's have a look at it here. We see that the gate went down. Gate to source is now 2 volt. We have the voltage across the transistor is now 7.2 volt. This is the 2 volt plus the 5 volt. So we are in the linear region. So actually the transistor is now dissipating power because there is a voltage across it, and we have the inductor current here going this way. The current in this branch is rather small. Okay, so most of the current is actually going this way, and lo and behold, the current in this resistor is only 1.8 milliamp, and this is because we have 2 volts minus VD. This is the voltage across the resistor, the 2 volts minus the voltage drop on the diode, which brings us to about 1.8 milliamp. So we see that the situation here is that the transistor is actually in the linear mode. It is dissipating power, and the current of the inductor is going out linearly because there is a constant voltage on it, that is the minus 2 volt or about minus 2 volt. Now what will happen if I'll remove the resistor, put a short here, it's a 1 milliohms, like a short, so I have only the diode. In this case, the voltage cannot reach minus 2 volt, okay? It'll be only the voltage on the diode, like 0.5 or something like that. And therefore the transistor will not enter the linear mode, and consequently the current now will be circulating here while the transistor is off. So it will be a different mode of operation, very similar to the case in which the transistor is in the bottom and the inductor is on the drain side. So this will be the case in which the voltage at the source is below minus 2 volts. So let's calculate the power dissipated by the transistor during this turn off process. The voltage is VDD plus 2 volt. We have 2 volts here. And the average current will be I peak over 2 during the period. So this will be the power. And the time it'll take depends on I peak and this 2 volt. Okay, so this is from V is equal to L the IDT. And this brings us to this expression here. When comparing this expression to the power that will be dissipated in the resistor plus diode in this other topology, which is the I square L over 2, this is the power stored in the inductor. We see in this case that during the turn off, a higher power is dissipated, which is dependent on VDD. So let's go back now to the questions of the riddle. The first one is, why is the resistor current low? Well, the reason is that the voltage across the resistor is 2 volt minus VD, the diode, and this actually limits the current to about 1.8 volt. This is the inductor current is not passing through this resistor. Second question was, where is the inductor energy dissipated? Well, in this case, obviously, it is in the MOSFET. In fact, the MOSFET is also dissipating a higher power because the source is still feeding power to the system. So therefore, the MOSFET is dissipating both the inductor energy plus the energy coming through this discharge period from the source. And finally, there was the question, what are the options for changing the resistor current magnitude? I'm showing here one example. If the gate voltage doesn't go to 0 but rather to negative voltage, then for the same VGS of 2 volt, S1, the voltage at the source, will be more negative. In fact, this will be this value here. And then the voltage on the resistor will be minus the voltage of the diode. So a bipolar drive will increase the current of this resistor, assuming it is 1K. So this brings me to the end of this presentation. I hope you found it of interest. Thank you very much.